The derivative is the centerpiece of calculus. It's the crown jewel. And I hope in this short video to give you some sense of what the derivative is all about. So to begin with, I want to show you a puzzle where the idea of this puzzle is that you need to find the relationship between the blue graph and the red graph. I have many examples. So here I show 3 examples. On the next page I have 2 more. And the idea is, can you figure out how is the blue graph related to the red graph in each example? The relationship is the same throughout each of these graphs. Okay. Now, if you like puzzles, here I'll show you the next 2 examples. Okay. If you like puzzles, I hope you pause this and try to figure it out on your own. I'm going to walk you through it. So notice that, let's look at this first example. First thing you might notice is that, let's say the horizontal axis here, I'm just going to call that time. I'm going to say at this time something happens, at this time something happens. Okay, notice that both of them transition at the same time. All right, so you have, the red one's moving along, not doing much, then all of a sudden it jumps. And at that same point, you get the blue one reaches a corner. Same thing at that jump, there's a little corner there. That jump, there's a corner. So we see something is happening in relationship between the 2. Now in the other examples, that's not so obvious because there aren't any corners. They're both moving all the time. In fact, if you were to tell me, if you wanted to tell me what the simplest relationship is here, you'd just say that the blue is the red one shifted over to the right. All right. But in this puzzle, the relationship between the blue and the red is the same in all examples. The next thing we might notice is this. When the red one is positive, it's above the 0 line, the blue is moving up. And when it's negative, the blue is moving down. When it's not quite so negative, the blue's not moving down quite as quickly. It goes back up to positive, and the blue's moving up. And that's really the key relationship we're looking for. Think of a person running on a field, say a football field, and the blue is measuring their position along that field. So red is telling you the speed they're running, and blue is saying how far they've run along the field. Here they're running, and then at some point they stop and they start running backwards because their speed went to negative. Then at some point they slow down, they get tired here, and so their speed is, their distance is decreasing slower. And then again they turn around, they start running forward. The red is indicating the rate at which the blue one is rising or falling if the red is negative. Let's check if that's true in our other examples. So here, what we should really check is the red, again, is remember, the rate that the blue one is changing. So when it's 0, we should see that the blue one is flat. And indeed, that's correct. Here, red is 0 again, the blue is flat. Red is 0, blue is flat. We should also see that if the red is negative, the blue one is coming down. And if red is positive, see it's positive between here, the blue one is coming up. So indeed, this does have that relationship where the red indicates the rate at which the blue is increasing. Now, this happens to be the equation, the graph for cosine, and this one happens to be sine. They happen to have that relationship. Now here, again, the red is always positive here. That's the rate. That means that the blue one should always be increasing, and indeed that's true, except for it's flat right there where the red one happens to be 0 momentarily. All right, if we go to the next examples, we see this is the exponential function. It just continues to increase. And we see that the value itself and the red curve, which tells you the rate at which it's growing, both follow the same trajectory. All right, now this is a lot like the first example. It's even simpler. The red is 0, so blue is doing nothing. Then the red jumps up to some positive rate. The blue is increasing, and then it stops, and the blue is flat again. So derivative is all about the slope. Okay, so we first should talk about the slope. Now, from algebra, you're familiar with slope of a linear function. So in other words, if you have y equals ax plus b, this is affine, but usually it's called linear. And that's something like this, some straight line, where you cross the y-axis. This is the y-axis, this is the x-axis. You cross the y-axis at b, and it has a slope of a. You call that the slope. Now, what is the slope? The slope is defined as the rise over the run. So, in other words, take any 2 points here. The run is this part. How far did you move to the side in the x direction? And the rise is how far did you move up? So a slope of 1, this graph looks kind of like a slope of 1. A slope of 1 is a 45-degree angle. So yeah, let's get another graph out here. Okay, slope of 1 is 45-degree angle. A slope of infinity goes straight up. A slope of 0 is just flat. And negative slopes go down. Okay, negative 2 would be something like this. Okay, so that's what slope is of a straight line. Now let's do something a little more interesting. Let's look at this equation, x squared. By the way, I'm often going to call an equation a function. So there is the origin. That's x equals 0, y equals 0. And we have a couple of points that we know. Let's say this here is x equals 1, y equals 1. Okay, so that would be 1 there. And up here, something like x equals 2 and y equals 4. Of course, you've got 0, 0. And it's symmetric in the sense that here, when x equals negative 1, you have y equals 1. Okay, so this is not a straight line. It doesn't have one slope throughout. However, you can talk about the instantaneous slope, and here's what I mean by that. Suppose we want to know at the time when x equals 1, what is the instantaneous slope? And the way you could get that is you could draw a line that approximates your graph at that point. Okay, so here's a straight line. This is called the tangent line. And the tangent line at that point is the best approximation to your actual function, x squared. If you zoom in right here, zoom in close enough, they'll look the same. That's the definition of the tangent line. All right, now this tangent line has a slope. And I've actually been careful of how I drew this because I know that the tangent line is actually going to cross x equals a half. So let's calculate the tangent line for the tangent line that crosses x squared, that touches x squared at x equals 1. So the slope equals the rise. What's the rise? Well, it goes from 0 to 1, so 1 over, and the run goes from half to 1, so that's a half, equals 2. So the slope equals 2, but this is only at one point in time, at x equals 1. If we want to pay attention to the fact that the slope changes with time, what we've calculated is, here's the derivative. The way that you usually write that is you just put a prime. You say x squared, and you put a little prime. It's faster than writing derivative of x squared. So we know that at x equals 1, this should be 2. Here's 2. Y equals 2. Now, let's just eyeball some other slopes. What should the slope be when x is 0? Well, it's flat, so the slope should be 0. We know that. And what is the slope when x is negative 1? So by symmetry, we know, well, it's the same slope except it's coming down, so it's going to be negative 2. All right? So negative 2. All right, so with that, looking qualitatively at it, you can see the slope is going to somehow increase. It just keeps getting higher and higher. But we don't know how. It could meander its way on between these points. Who knows how it gets there? All right. We could go carefully calculate it for each point, get more dots to connect. Turns out there's a rule that says the derivative of x to the p is always going to, where p is just any number you want, is always going to be p times x to the p minus 1. So in our case, we started with x squared. And if you follow this formula, you get 2 times x to the 2 minus 1, which is 1. You don't write it. So it's just 2 times x. So what we found, so this formula says that we actually know what the slope is for all x. It's 2 times x. So in other words, this squiggly line is actually not squiggly at all. So for this particular example, the slope grows linearly at the rate 2 times x. That's the magic of calculus, is that you get these simple formulas to get the slope at each point.